with what is going on, okay, we are going to focus at point Q. So point Q is our reference point, yes or no? So now we put our finger at point Q. P will induce a moment about this direction, yes or no? Okay, then you have a counter moment coming in. Okay, so now, good point, I have not thought. So we are focused, or the analysis is done relative to point Q. Okay. Why? Because I'm going to write the next statement, which states that moment at point Q is equal to minus Py. Okay, we are focusing on the analysis at point Q. Okay. So the next thing we're going to apply, the next thing we're going to do is we're going to apply. Probably you have seen this in math, okay? We are going to apply the elastic curve equation to relate bending moment to deflection. Now, question, have you all seen the elastic curve equation before in math? This is probably you all learned last term when I was teaching you all 2Q, yes or no? You all recall or no? If I write out the general equation, so the elastic curve theory specifies that the second moment of area and Young's modulus is equal to d squared y over dx squared is equal to m. Have you seen this before? Hey? Yes? Which course did you all take that you all see this? Can you remember? 2Z, right? So can you all refer to okay, can you all refer your notes in 2Z, please? Okay. Okay, it's okay. It's okay. Okay, if not, explain, it's fine. Okay, I'm just going to apply it. Use it. So this is known as the elastic curve. Okay, elastic curve. So this is known as the elastic curve equation. Okay. So what good is this elastic curve equation? Okay, what good is this elastic curve equation? So I'm gonna show you the application first. Okay, then we are going to come back to columns. Okay, so let's focus on the elastic curve theory. Or application. Hey, I cannot spell now. So the equation of the elastic curve theory is, so the elastic curve theory is what? EI d squared y over dx squared is equal to m. Okay. So now I want you to consider, okay, I want you to consider where you have dv over dx is equal to minus omega as a function of x. Okay, so let's think about a structure that is very simple. Okay, so we consider a structure this structure is free at point A, and then at point B, it is built in, and then you have a distributed load over here, and the distributed load is omega naught, and the distance from here to here is L. So from here, we derive the equation where we have omega as a function of x is equal to what? Omega naught over Lx. Okay. Then what do? Is we have dv over dx is equal to minus omega as a function of x. This is equal to minus omega naught x over L. Now, I want you to, minus. Okay, I want you to memorize this. Okay, x is equal to naught, x is equal to L. Okay, and I want you to write in the boundary condition in this format: V, M, theta, L. Right hand side is also V, M, theta, L, and theta L. Eugene, seriously, theta Y. Okay, I want you to write that in that sequence, and I'm going to explain your why later on. From here, we know that V as a function of x is equal to what? Is equal to minus omega, or let me write this out, where you integrate minus omega naught x over L dx. So what do you have over here? Minus omega naught x squared over 2L plus by what? C1. And this is also equal to what? dm by dx. Bear with me, okay? From here, we can again find m as a function of x. We integrate what? Minus omega naught x squared over 2L plus by C1 dx. This in turn will give you minus omega naught x cubed over 6L plus by C1x plus by what? C2. And we now know that this is equal to EI d squared y over dx squared. This is where we apply the elastic curve equation. This is where we apply the elastic curve equation. So from here, we have EI d theta over dx. We integrate again. We integrate minus omega naught x cubed over 6L plus by C1x plus by C2. So this is equal to minus omega naught x4 over by 24L plus by C1x squared over 2 plus by C2x plus by C3. And finally, we have EI y. We are going to integrate our minus omega naught x4 over 24L plus by C1x squared over 2 plus by, I don't know why I teach this course. So this is equal to minus omega naught x5 over, I can't go, 120 L plus by C1x cubed over 6 plus by C2x squared over 2 plus by C3x plus by C4. And y, I'm going to copy the whole thing. Okay, I'm going to copy the whole thing. The integration part is easy. Okay, the integration part is easy. Okay, we know that the integration part is easy. Yes. Oh yeah, EY over dx. Yeah, thank you. And this is in fact equal to EI theta. Okay. To apply this technique, as you can see now, you need to know your what? Boundary condition. Again, I'm going to emphasize on what? Boundary condition. All these methods is absolutely useless when you have not a clue about what? Boundary condition. Are we clear? Okay. All these are absolutely useless. Okay. How many unknowns? How many unknowns? 4 unknowns. How many of you are taking numerical methods now? Some of you, I saw earlier, Dr. Chris Norton was here. You're taking numerical methods. 1 unknown, sorry, 4 unknown, 1 equation. How can you solve it? Using numerical method, what will you use? Rangapata 4th order, for example. Okay, so you can solve this numerically, but we are not there yet. In order to solve 1 equation with 4 unknowns, how many boundary conditions do you need to know? Yes, 4. Okay. Now let's look at this. When x is equal to 0, what is your shear force equal to? Anyone? 0. When x is equal to 0, what is your moment equal to? Anyone? Don't be shy. Come on. When x is equal to 0, what is your moment equal to? 0. Why? When you remove the support at A, what will happen to the structure? It's equal to 0. Theta, some of you might ask me, Eugene, what is theta? Okay. So if we were to sketch, if we were to sketch, if we were to sketch the elastic curve theory, if this is x, this is y, this is the deformation of the structure. Okay. So theta, let me draw this better. Okay. So if we look at this point, okay, that's an arbitrary point that we are looking at. And then I draw a horizontal line and I will sketch a tangent to this point over here. This is what theta is. Okay. So now, you know what is theta now. Coming back to here, can someone tell me when x is equal to L, what boundary condition do we know? I repeat again, when x is equal to L, what boundary condition do we know? Y is what? Deflection, yes or no? So is there any Y movement if this is my X and this is my Y? Anyone? So we know that is equal to what? 0. We only know what? How many boundary condition? 3 boundary condition. Okay. Whenever I do this, it don't work. Let me try. We need to find one more boundary condition. Okay. Where my I don't to start drawing walls or what. Oh, by the way, I got warned not to draw on walls also. I got warned, okay. The next time I drew on wall, they were clean and they will deduct from my payroll. Who really cares? That means something at point B. At point A, it can move. That means something about point B. Hurry up. It's not easy to bend this. Yes. Obvious or not obvious? What's the moral of the story? Bring a ruler for your term test. Can you see this? Yes or no? Okay. Be clear. Now, I love this course like crazy.